Hello everyone, welcome to another exciting math problem of the week. Today's problem involves number theory, which may be a bit challenging for beginners. Here is the problem. How many positive integers n such that 2 to the power of 20 plus 2 to the power of 24 plus 2 to the power of n is a perfect square? The options are A 1, B 2, C 3, D at least 4. Before we uncover the solution, I encourage you to hit the pause button, grab your pen and paper and give it your best shot. When you're ready, feel free to share answers in the comment. Then we'll explore the solution together. Let's get started. Before we solve this question, let's look at a simple version of it, as shown. The only difference is here. We change the number 24 to 23. Suppose we have an equation where m squared equals 2 to the power of 20 plus 2 to the power of 23 plus 2 to the power of n. Factor out the common exponent. We notice that 2 to the power of 20 can be factored out from the first two terms. This leaves us 2 to the power of 20 multiplied with 9 plus 2 to the power of n. We recognize that n is 3 squared. Some of you may recall that 3 squared plus 4 squared equals 5 squared, thanks to our old friend, the Pythagoras theorem. Then multiply each term by 2 to the power of 20 and compare the terms. We obtain 2 to the power of n is 2 to the power of 24, and hence n is 24. We wonder if n equals 24 is the unique solution. To answer this, let's try the following. Write 2 to the power of 20 times 3 squared as 2 to the power of 10 times 3, the whole thing squared. Then 2 to the power of n is a difference of 2 squares. Apply the formula a squared minus b squared equals a plus b times a minus b. We obtain the following. Hence, we may let n plus 2 to the power of n times 3 be 2 to the power of k, and n minus 2 to the power of 10 times 3 be 2 to the power of n minus k for some integer k where k greater than n minus k. The difference of these two equations gives the following. Solve it and we obtain k equals 13 and n equals 24. We show that n equals 24 is the only solution. Compared to this version, our original question is not too much different from it. I'll show you 3 answers using the same technique. That is, 1 plus a squared equals 1 plus 2a plus a squared. So we suppose that m squared equals to the expression shown. Factor out 2 to the power of 20, we have the following. As we want to obtain the form 1 plus 2a plus a squared, we write the expression as follows. Here, 2 to the power of n minus 20 equals 2 to the power of 6. Then we are able to write the expression as a perfect square if n equals 26. We apply the similar method again, but switch the position of 2 to the power of 4 and 2 to the power of n minus 20. Write it as the form 1 plus 2a plus a squared. We successfully make it as a perfect square if n equals 23. Next, we assume that n less than 20 and factorize 2 to the power of n. Apply the same method and we obtain n equals 14 for getting a perfect square. So far, we obtain 3 answers, n equals 14, 23, and 26. Next, we make an assumption that n is at least 20 and factorize 2 to the power of 20. Then combine the first and second terms to get 17. Now we need 17 plus 2 to the power of n minus 20 to be a perfect square. By trial and error, it is not difficult to get 2 more solutions. They are n equals 25 and n equals 29 as shown. This means that the correct answer is D at least 4. a big thank you to everyone who submitted their answers. This time around, only 45% of the respondents answered the question correctly. Although we obtained the answer to this problem, but we still wonder how many solutions can it have. There have been some discussion after the inspiration from Ramanujan square equation, and they are known to be a special type of equation that attract researchers' interest. This Diophantine equation of the form y squared equals to 17 plus 2 to the power k was solved in 1981, and it was shown that there are only 4 solutions. Our question is slightly more than this form, as n can be less than 20. Thank you all for taking part in this math challenge. Stay tuned for more intriguing math problems. This concludes today's lesson. I hope you found this video insightful and are looking forward to more medical adventures. Until next time, take care and bye-bye.